Hello and welcome to this brief presentation related to the quantities of mass, weight or weight force, and density. Within this presentation we'll define each of the terms, state appropriate equations, and then solve some engineering problems related to these quantities. Let's introduce the quantity of mass and weight or weight force. Any particular object has two attributes, that of mass, usually symbol M, and weight, symbol W. Mass is defined as the quantity of matter, how much of it there is. If we move an object, even taking it to the moon, this does not change the quantity of matter, so the mass is constant. Mass is defined as a scalar quantity, and so it has a magnitude, that's a value or a size, but no direction. In the SI system, mass has the unit of the kilogram, kg. It should be noted that masses can also be expressed in tons or megagrams, where 1 metric ton is equivalent to 1,000 kilograms, and 1 megagram is also equal to 1,000 kilograms. Objects near the Earth experience a pulling force towards the Earth. This pulling effect is due to the acceleration of gravity, symbol G, and for calculation purposes it's considered to be equal to 9.81 meters per second squared on Earth. The effect of gravity acting on an object is to produce a force on the object, and this force is known as the weight, sometimes called the weight force. The SI derived unit of the force is the Newton, and given a symbol N. Now, if the mass is taken to the moon, its weight force is now less than on Earth because the moon's gravity, that's its pulling effect towards the centre of the moon, is approximately 1/6 of that on Earth. So the moon's acceleration due to gravity is 1/6 of 9.81, so approximately 1.635 meters per second squared. The relationship between mass and weight of an object is expressed by the equation W is equal to M multiplied by G. This is actually Newton's second law, force is equal to mass times acceleration, where M is the mass of the object in kilograms and G is the acceleration due to gravity. It's important to remember that the direction of the weight force is always downwards. Let's also consider the quantity known as density. This is actually mass density, and often given the symbol rho, that's a Greek symbol. If the mass of an object is unknown, it can be found from knowing the density. Density is a measure of the quantity of matter in each unit of volume. So density is defined as mass divided by volume. So density, symbol rho, is m upon v. Note that the volume in the SI system has the unit of the meter cubed, and the SI system, which is a coherent system of units, we can always find the unit of a particular quantity from the formula. So in this case, the derived SI unit for density is mass over volume. Mass would be in kilograms and the volume is in meters cubed. So the unit of density is kilograms per meter cubed. Notice it can also be written as kilogram meters to -3. It's the same unit written using a negative index. Here are some typical values of density, and there are actually 3 different types of density shown on this slide. The first density is the one we will consider in this presentation, and that's the mass density, or simply known as the density. That's symbol rho. We stated previously the unit of mass density is a kilogram per meter cubed, or kilogram meters negative 3. And in this column here, I'm showing you typical values for various solids and liquids. The next column shows relative density, sometimes termed as specific gravity. The symbol for relative density is the lowercase sigma, and that's equal to the density of a solid or liquid divided by the density of water. The density of fresh water at 4 degrees C is typically stated as 1,000 kilograms per meter cubed. So to find the relative density, we simply divide the density of the other solids or liquids, shown in the table, by 1,000. So the mass density of aluminium is stated as 2,720 kilograms per meter cubed, but that'd be a relative density of 2.72. In other words, dividing the mass density by the 1,000. And that's the same for all the values in this column. Just note for reference that only solids and liquids are defined relative to water. Gases are actually relative to air. And the final column shows another density, termed the weight density or specific weight. That's usually given symbol omega, and that's equal to the mass density multiplied by the gravitational acceleration. So this formula changes the mass density into a weight density. So the units of weight density would be newtons per meter cubed or newtons meters to negative 3. Here you can see we simply multiplied the mass densities by 9.81. So for example, the mass density of steel is 7,840 kilograms per meter cubed. Multiply that by 9.81, then the weight density is 76,910 newtons per meter cubed. This slide shows you the actual calculations here to determine relative density. We simply divide our mass density, shown here, by the density of water, shown here. That produces, in this case, the relative density, shown here. And again, for steel, 7,840 is the mass density. Divide that by the density of water, we determine the relative density. This slide shows the calculation for weight density. So the aluminium mass density is 2,720, shown here. We simply multiply that by the acceleration of gravity, 9.81, and we find the weight density, shown here. And again, considering steel, the mass density is 7,840 kilograms per meter cubed. If we multiply that by the gravitational acceleration, we find the weight density in newtons per meter cubed, shown here. So those slides are just showing you that there are more than one density, so be careful when you're extracting information from various reference sources that you know which density you're actually considering. In this presentation, we will use the mass density within our calculations. And also be aware of the differing units of mass density, symbol rho. I've shown here unity bracket conversions. We considered unity brackets in a separate presentation and are often very useful for undertaking conversions, which we have on this slide. But I just want to bring your attention to the various units of density. So for example, if we have a mass density of 7,840 kilograms per meter cubed, that's actually steel, then that can be shown using a unity bracket to be equal to 7.84 tons per meter cubed. This time we're converting the mass density of steel into megagrams per meter cubed, and that evaluates to be 7.84 megagrams per meter cubed. Converting the mass density of steel now into grams per centimeter cubed, that evaluates to 7.84 grams per centimeter cubed, again using our unity bracket method. So in essence, 7,840 kilograms per meter cubed is the same mass density as 7.84 tons per meter cubed. is the same mass density as 7.84 grams per centimetre cubed and the same mass density as 7.84 megagrams per metre cubed. And again, that's just for reference, but these various units are often used within engineering. For the rest of the slide, we're going to consider some calculations involving these various quantities. And I've put on this slide some of the basic formulas that we'll be referring to for reference. So we've got our weight formula. Weight is mass times gravitational acceleration. We have our mass density formula. Density, symbol rho, is mass divided by volume. And I've also included here the volume of a rectangular block. V is equal to B multiplied by D multiplied by L, where B, D and L are shown here on my diagram. Because in some of the questions we'll consider, we will have a rectangular section. But of course, in reality, our problems can be associated with various sections, for example, cylindrical sections. But in these questions, we will just consider rectangular sections. So the way the rest of the presentation is devised, I'm going to state questions on the slide. I would encourage you to stop the presentation and attempt the questions, but on the following slides I will show the work solutions. So here's the first batch of tutorial questions related to mass and weight. Question 1. A particular piece of scientific apparatus has a mass of 3 kilograms. We're asked to calculate the weight on Earth of the apparatus. If the apparatus is taken to the moon, we've got to state what the mass is on the moon, and then we've got to calculate the weight of the apparatus on the moon. Question 2, we're told that a person's weight on Earth is 873 newtons. We've got to calculate the person's mass. And then question 3, the mass of a typical eating apple is approximately 0.1 kilograms. We've got to find the approximate weight of the eating apple. The answers are shown in the brackets on the right hand side. I'd encourage you to stop the presentation and attempt these questions. The full work solutions are shown on the following slides. Okay, so question 1a is the solution. Our particular piece of apparatus is 3 kilograms, so my mass of 3 kilograms on my apparatus. The first part of the question, we're asked to calculate the weight on Earth, so it's simply going to be weight is equal to mass times the gravitational acceleration of the Earth. So the mass in this case is 3 kilograms, gravitational acceleration 9.81 meters per second squared. So multiplying the numbers, the weight on Earth of the apparatus is 29.4 newtons. Part 2, the apparatus is now taken to the moon. What's its mass on the moon? Well, the mass of the apparatus on the moon will be the same as that of the apparatus on Earth, because mass is a quantity of matter, how much of the object you have, and that won't change by being taken to the moon. And question 1, part 3, we're asked to find the weight of the apparatus on the moon. Well, we know the gravitational acceleration on the moon is 1.635 meters per second squared from our previous slide. So the weight on the moon, again, is the mass times the gravitational acceleration on the moon. So 3 kilograms multiplied by the 1.635 meters per second squared, so 4.9 newtons on the moon. In other words, a sixth of the weight on Earth. So question 2, the person's weight on Earth was 873 newtons. Going to calculate the person's mass. So remember, our weight force always acts vertically down, so the 873 newtons, shown here as a downward direction. We've got to calculate the person's weight force. We've got to calculate the mass. We know that the weight force is equal to mass times gravitational acceleration. So rearranging for mass, we simply divide both sides by the g. So the weight force divided by the gravitational acceleration, 873 newtons divided by 9.81 meters per second squared acceleration. That evaluates to 89 kilograms. So the person's mass on Earth is 89 kilograms. Question 3. A typical eating apple is approximately of mass 0.1 kilograms. We've got to find the approximate weight. So to calculate the weight of the apple, we know weight force is equal to mass times gravitational acceleration. In this case, the mass is 0.1 kilograms. So it evaluates to a weight of approximately 1 Newton. Here are tutorial questions 4, 5 and 6. Question 4a, we're asked to determine the weight of the following items. So part 1, we've got 5 1 kilogram bags of sugar. Part 2, we've got 1 50 kilogram bag of cement. Part 3, a typical family house has a mass of 100 megagrams. And part 4, a Boeing 747 aircraft has a takeoff mass of 362 tons. We've got to calculate the weight of each of those items. Question 5a, we're asked to determine the volume and mass of a concrete column which has dimensions 1.5 meters wide, 1.25 meters thick, and 8 meters high. So it's a rectangular column. We're given the density of the concrete and it's 3,000 kilograms per meter cubed. And question 6, an aircraft fuel tank is designed to carry 6,000 kilograms of fuel. If the fuel density is 750 kilograms per meter cubed, we've got to calculate the volume of the tank required. Again, the answers are shown in brackets on the right hand side. I'd encourage you to stop the presentation and attempt these 3 questions, but the full work solutions are shown on the following slides. So question 4a, part 1, we're asked to find the weight of 5 1 kilogram bags of sugar. So our 5 bags of sugar, the weight force is equal to mass times gravity. The mass in this case will be 5 multiplied by the 1 kilogram, 5 kilograms, multiplied by 9.81. So the weight of the 5 1 kilogram bags of sugar is 49.05 newtons. Part 2, we're asked to find the weight of a 150 kilogram bag of cement. So again, from W equals mg, the mass this time is 50 kilograms multiplied by 9.81 meters per second squared. So the weight of 150 kilogram cement bag is 490.5 newtons. Question 4a, part 3. We're asked to find the weight of a typical family house having a mass of 100 megagrams, which seems an extremely large mass for a typical house. But anyway, we're asked to find the weight of the house. So solution to part 3, the 100 megagram house. Firstly, as we noted previously, 1 megagram is equivalent to 1,000 kilograms. So in this case, the mass of the house is 100 times 10 to the 3 kilograms. Weight is equal to mass times gravitational acceleration. So the mass in this case is 100 times 10 to the 3 kilograms, and that's multiplied by 9.81 meters per second squared. So the weight of our house is 981 kilonewtons, or 981,000 newtons. And finally, question 4a, part 4. We're given that the Boeing 747-400 aircraft has a takeoff mass of 362 tons. Again, we have to convert this into a weight. So, given the aircraft mass is 362 tons, converting that into kilograms, there's 1,000 kilograms in 1 ton, so the mass is 362,000 kilograms. Multiply that by 9.81 meters per second squared, we can find the weight, and the weight force is 3.551 meganewtons, or 3.551 times 10 to the 6 newtons. Question 5, we're asked to determine the volume and the mass of a concrete column having dimensions 1.5 meters wide, 1.25 meters thick, and 8 meters high. We're given the density of the concrete is 3,000 kilograms per meter cubed. So the first thing to do is extract the information from the question. Here's my diagram with my 3 dimensions. I've called the first dimension 1.5 meters my B dimension of the column, the 1.25 meters thick. I've called that D here, and it's 8 meters high, so that's the length L. We know the concrete has a density of 3,000 kilograms per meter cubed, and that's shown here. So just for a moment, let's think through the solution here. We're asked to find in the question the volume and the mass. So volume occurs here in our equations and also here. So given in the question the width, the thickness and the height of the column, I can find the volume. I can put the volume into this equation here. I know the density, so that means I can find the mass of the concrete column. So here's the first calculation to find the volume of the column. That's V is equal to B multiplied by D multiplied by L. So putting my figures in, that produces a volume of the concrete column of 15 meters cubed. Part 2 of the solution, we want to find the mass of the column. From density equals to the mass over volume, we can rearrange to find the mass. That's density multiplied by volume. So the density is 3,000 kilograms per meter cubed, multiply that by 15 meters cubed. That evaluates to 45 megagrams. Question 6a. The aircraft fuel tank is designed to carry 6,000 kilograms of fuel. The fuel density is given as 750 kilograms per meter cubed. We've got to calculate the volume of the tank required. There's information extracted from the question. Again, if we just think through for a moment how we're going to solve this problem, what are we given in the question? We're given the mass, so I have the mass here. We're also given the density, so I can transpose this equation to find the volume. So rearranging for V here will provide me with the answer. So question 6a continued. We have to find the volume of the fuel tank. So from the density is equal to the mass divided by the volume, we can rearrange the equation. Volume is equal to the mass divided by the density. In this case, the volume is equal to 6,000 divided by 750. So that evaluates to 8 meters cubed. And here's the final batch of tutorial questions. Question 7, part 1, we're asked to estimate the mass, and in part 2, the weight of the air in a room that measures 5 meters by 4 meters by 2.5 meters. We're given the air density as 1200 grams per meter cubed, so we need to be careful with the unit given. Question 8, a small block of pine timber and a block of steel have the following dimensions: 150 millimeters by 50 millimeters by 10 millimeters. The densities of the wood and the steel are 3,850 kilograms per meter cubed and 7,840 kilograms per meter cubed respectively. We've got to determine the mass and the weight of both the pine and the steel blocks. And finally, question 9. A builder orders 2 meters cubed of sand. The mass density of the dry sand is 1.6 grams per centimeter cubed. We've got to calculate the mass of the sand, assuming it's dry. Again, answers are stated in the brackets on the right hand side. I would encourage you to stop the presentation and attempt these 3 questions, but the full work solutions are shown on the following slides. So, question 7, we're asked to estimate first of all the mass and then the weight of the air in a room, 5 meters by 4 meters by 2.5 meters. I show my diagram here of the room and the dimensions, the B, the D and the L as stated in the question. Notice that the density of the air was given as 1200 grams per meter cubed. I've divided that by 1000. My mass density rho is 1.2 kilograms per meter cubed. Just be careful there. So again, briefly thinking through what we need to find here. We're asked to find the mass and the weight. So we need to find the mass here and the weight here in our equations. What we're given in the question, well, we've got the dimensions B, D and L for our rectangular room. So that means we can find the volume. We've also been given a mass density here. So once I've calculated the volume of the rectangular block, I can put it in this equation. I can rearrange the equation to find the mass. And once I've found the mass, I can put it into this equation and then multiplying by gravitational acceleration, 9.81 meters per second squared, I can find the weight force. So that's my thinking steps for the solution to this problem. So let's find the volume of the air. The volume is B multiplied by D multiplied by L. Multiplying our three dimensions together, the volume is 50 meters cubed. So we can now find the first part of the question. The mass from density, rho, is equal to the mass divided by volume. Rearranging or transposing the equation, the mass is equal to the density multiplied by the volume. Density is given here, 1.2 kilograms per meter cubed, so for a density, volume calculated above, 50 meters cubed. So the mass of the air in the room is 60 kilograms. And then the second step, we need to calculate the weight of the air. So the weight is simply the mass times the gravitational acceleration. The mass we've calculated here at 60 kilograms. We always assume 9.81 meters per second squared for the gravitational acceleration on Earth. So the weight of the air in the room is 589 newtons. So in question 8, we're given a small block of pine timber and a block of steel. They've got the same dimensions, 150 millimeters by 50 millimeters by 10 millimeters. And we're given the densities of the wood, the timber, and the steel, 3,850 kilograms per meter cubed for the timber and 7,840 kilograms per meter cubed for the steel. We have to determine both the mass and the weights of the pine and the steel blocks. So just for a moment, thinking through the question, what are we given in the question? Well, we have the density of both the pine and steel blocks. Given the dimensions in the question, they're rectangular blocks, so we've got the B, the D and the L given in the question, so we can find the volume. So from finding the volume, we put that into this equation here. We can then rearrange to find the mass. We put the mass into this equation here. We can calculate the weight force. So that's our plan of attack through the question. So here's my two blocks, the timber block and the steel block here. They've got the same geometry, but the densities are different. The density of the timber is 3,850 kilograms per meter cubed. The density of the steel block is 7,840 kilograms per meter cubed. Notice that I've placed all the dimensions in terms of meters because the densities are in terms of kilograms per meter cubed. So my geometry is in meters. I need to do that to avoid inconsistencies in my units. So now we can calculate the mass of the timber. Mass is the density multiplied by the volume. Density is given in the question, and we just calculated the volume above, the meters cubed. So we can calculate the mass, which is approximately 0.289 kilograms. And for the steel block, we can calculate the mass. Same process, that works out to be 0.588 kilograms. And finally, the weight of the timber, weight is mass times gravity. That's the value of mass given above here. I've used the accurate value here. Multiplied by 9.81 meters per second squared as always. So the weight is 2.83 newtons to 2 decimal places. And then calculating the weight of the steel, same formula, just a different mass to use here. So the weight is 5.77 newtons to 2 decimal places. And finally, question 9. A builder orders 2 meters cubed of sand. The mass density of the dry sand is 1.6 grams per centimeter cubed. we've got to calculate the mass of the sand, assuming it's dry. So information given in a question, we've got the density, although it's not in the units we need, but we have the density. We're given the volume explicitly this time. We're asked to find the mass, so we simply have to transpose this equation to find the mass. Firstly, though, I've converted the density of the sand from grams per centimetre cubed to kilograms per metre cubed. I'm using the unity bracket here to undertake the calculation. We considered the use of unity brackets in a previous presentation to undertake conversions. Always remember that they're cancelling unity brackets. So for example, because in the first unity bracket here, we've got to convert the grams to kilograms. So we've got to cancel the grams. So our unity is 1 kilogram is 1,000 grams, but the 1,000 grams has to be on the bottom of the bracket to cancel the grams on the top of the density here. And similarly, if we want to convert the centimetres to metres, then our unity bracket is 100 centimetres is equivalent to 1 metre. But again, because they're cancelling brackets, the centimetres have to be on the top line to cancel to leave us with metres on the bottom. And of course, in this case, the centimetres are cubed, so we must cube the unity bracket. So to convert the 1.6 grams per centimetre cubed, we have to divide by 1,000 and then multiplied by 100 cubed. That's using our unity bracket. So the density of the dry sand is 1,600 kilograms per metre cubed. So to work out the mass of the sand M, we know that would be the density multiplied by the volume. We have our density calculated above. Volume was given in the question. That evaluates to a mass of 3,200 kilograms, or if you want to state it in megagrams as the answer is in megagrams, that would be 3.2 megagrams. Here's the bibliography used to help generate this presentation. Hope this has been of interest to you, and thank you for viewing.